So we're going to talk about aldehydes, ketones, and carboxylic acids in this part. And one of the common features of these is this group called the carbonyl group, and it is going to contain that carbon to double bonded oxygen. So it's a common factor, and all of these have this group in it. And one of the big things that we need to know about it is this oxygen is going to pull electrons from the carbon because of those electronegativity differences. So we'll have partial positive charges. We'll have partial negative charges on this oxygen, partial positive charges on this carbon. And this carbon also is going to have a structure that's a 120-degree bond angle. So it's going to be trigonal planar, and it's also going to be sp2 hybridized because one of the p orbitals is unhybridized in order to form that pi bond. So there are actually other groups that look similar to these, and so aldehydes, ketones, carboxylic acids are what we're going to focus on. There are also other functional groups called esters, and this has a chain where oxygen's in the middle of a carbon chain. So sort of like an ether, but it's called an ester because of that carbonyl group that's attached. And also an amide is another functional group we might see. These are the functional group that are found on the backbones of proteins that connect different amino acids together to form peptide chains. It's an amide functional group. In terms of understanding what a carbonyl functional group looks like and is, so I have this drawn out chemical formula for 4 different compounds. I want you to draw out their Lewis structure so you can determine if these have that functional group or not. And you should be able to identify this, and please answer this and post this in the Blackboard space, which of these contains a carbonyl group. Again, the aldehyde is when the carbon is attached as a primary carbon where that double bond is attached versus a ketone. This is a secondary carbon in the middle of a chain, and that is going to be the difference between an aldehyde and a ketone. We want to also look at, in terms of this question, which of these compounds is an aldehyde? And post your answer in our Blackboard space. And then for the next one, which is a ketone. So please post those answers in our Blackboard space. Naming aldehydes is a lot of times they're known for their common names. For example, formaldehyde is just a single carbon double bonded to oxygen. That's formaldehyde. Used a lot of times to fix tissues for analysis or to preserve them in solution. Acetaldehyde is a compound that we saw when we looked at the fermentation or the metabolism of ethanol, and this is a 2-carbon aldehyde. And then we also have a benzaldehyde shown here, which is kind of also the kind of flavoring of almonds or amaretto flavoring. So these are some simple and common aldehydes which have been named with these common names. We also have a way to name these using the IUPAC system. And here's an example of basically still finding the longest chain, but we're always starting that chain number on the carbonyl carbon. So here we would number from right to left, 1, 2, 3, and 4. So that's going to be our base, is the bute base. And we're going to say the 3-methyl. Here on the 3rd carbon is a methyl group, butan al ending. So instead of butene or butanol, we're going to have the butan al instead of ol. That would be for an alcohol. It's an al for an aldehyde. So now the al, we don't have to put a 1-butanal, for example, because we know we start this functional group. We start the naming or the numbering with that functional group. Formaldehyde is a colorless gas. It kills viruses, fungi, different bacteria with reactions by cross-linking nitrogen compounds and basically fixing them in space. So it's also used to fix tissues so that we can kind of absorb those or keep those tissues intact and kind of look at those in solution, for example, if we're fixing biochemical specimens. Ketones are that functional group where that carbonyl group is in the middle of a chain. Here's a common acetone is a common functional group. This is the common name for this one. And we can also see the IUPAC name here, methyl ethyl propyl. So you'll notice that prop is the backbone. And then the suffix is going to be the O-N-E ending, propanone. And we're telling us where that carbonyl group is with that number. So 2-propanone is the IUPAC name, acetone here is the common name. This is an example of acetone is a common nail polish remover. In our metabolism in our bodies, a lot of times when we're burning fats or the carbohydrate balance is out of balance, the carbohydrates are out of balance with diabetes, a lot of times different types of ketones or acetone are produced in the liver, and this condition is known as ketosis. It really can be severe if you're not able to kind of flush this from your system, and a lot of time the odor of acetone can be kind of perceived on a patient's breath. So it's interesting. This is a common metabolite in our bodies that kind of indicates something's going on with our metabolic state. For naming the ketones, we find the longest chain. We put that carbonyl group on the lowest number within the chain as possible. So we would count obviously from left to right here instead of right to left for these two groups here. And then we're going to put that number of that carbonyl carbon in front. So here's a methyl ethyl propyl, so 2-propanone, and then add that O-N-E ending instead of the propane, for example. Here we have the methyl ethyl ketone. So this is one more common way to do it, but the IUPAC naming system is 2-butanone. And then here we have a methyl ethyl propyl butyl pentyl. So we have a pentane backbone, and then we take off that E and then add the O-N-E ending. So pentanone, and that functional group's on the second carbon. Here's a cyclohexane, and we just add the O-N-E ending, cyclohexanone. We don't have to number it unless there are more than one functional group on here, and in this case there is not. All right, so we have 4 different compounds now, and I want you to, from left to right, I want you to think about which is the highest boiling point, which is going to have the lowest boiling point. What are your thoughts here and why? What is the rationale for your answer? So take a moment to answer this and think about the kind of rating these, and then we'll walk through that process. So butane, obviously the lowest boiling point, and that is because we are going to be only interacting with the van der Waals forces here. But in propanal, now we have some amount of polar bonds. So we are able to kind of pull some of the electron density out to the end here, and that's going to give it a little bit more those dipole-dipole interactions. So the boiling point will be a little higher. When we go to acetone, it's about the same as propanal. There's a little bit better. We have a little bit more of a structural kind of a geometric shape that allows it to better maybe interact with another acetone subunit. So the boiling point's a little higher, but these are about evenly matched here. And then we go to propanol, and that again, we have that ability to do the specific hydrogen bonding, the dipole-dipole, which is going to increase the temperature of boiling point quite a bit. What do you think about this one? Which of these compounds do you think would be soluble in water? Take a moment, think about that, and pause here, and then we'll talk about this. All of these groups, you'll notice, have the functional groups with oxygen in them. And because of that, they're all going to minimally have some ability to form dipole bonds. Earlier, I mentioned a 1:5 ratio. So you need, for every 5 carbons, we need 1 ability to kind of have this dipole-dipole interaction. And we only have 2 carbons here, 2 carbons here, 1 and 1. So since we have the ability, we have 1 of these in each of the compounds, 1 of those oxygens, it's going to be a better than 5:1 ratio. So all of these compounds in the solution are going to have the ability to interact with water through those dipole-dipole interactions. So again, as long as we think about that 1:5 ratio between the carbon and the oxygen within that compound, we should be able to have a water-soluble conditions for these types of functional groups. So they'll help with the solubility in water. Simple ketones are less toxic than the aldehydes. The aldehydes at the end of that chain just open it up for a lot more chemical reactivity to happen. Many of these also have distinct odors and flavors, and so many fragrances are due to molecules that contain these different types of compounds and functional groups. We spoke about this a little bit, but aldehydes, we can continue to oxidize those into carboxylic acid functional groups. We can add another carbon to oxygen bond, whereas the ketones, this does not happen. The other chemical reaction that I'd like to talk about now between aldehydes and ketones is called the reduction reaction. So we have the oxidation reaction, and then we have the reduction reaction, which is the exact opposite chemical reaction. These aldehydes, for example, are reduced to primary alcohols. And notice what we're doing is we're removing carbon to oxygen bonds. We're making different oxygen to hydrogen or carbon to hydrogen bonds. So we're adding hydrogen now to these groups, and typically something we're going to give some type of hydrogen bond in that chemical reaction or add that to the chemical reaction so that we can add hydrogen bonds instead of those double bonds. So we essentially are getting rid of that double bond by adding hydrogens. We'll notice that aldehydes turn into primary alcohols because of where that carbon is located. Ketones are going to turn into secondary alcohols, the same type of situation where we're adding a hydrogen to the oxygen and to the carbon, and we're breaking that double bond. Other reactions with aldehydes and ethanol, we can make these hemiacetyls, and this is where we're essentially creating this carbon is going to attach to this oxygen, and we're going to break that double bond to allow that to happen. And you'll notice that we get an alcohol functional group, and then we get an ether functional group attached. So this is actually called a hemiacetyl functional group. Half of this, so hemi is a half, and this is a acetyl group is a carbon OR group. And if we had a full acetyl group, that we would have a O and an R here, but it's only half. So that's why it's a hemi, is half of it. So hemiacetyls are when we're talking about this different types of function. And these are common, especially we'll talk about in a moment here, with these form in sugar molecules. And essentially this is the reaction. If you have an aldehyde, this can happen with an aldehyde or a ketone, where we have an alcohol group, and where the actually lone pair of the oxygen is going to be attaching to that hydrogen, and it's going to be then form this new bond here, and then the lone pair from the oxygen here is going to attach to that carbon, and that's where we create that new bond over there. And that's the process that's going to happen here in this setup here for the creation of our hemiacetyl group. The hemiacetyls, actually, if you're looking at an aldehyde or a ketone, here's an example with ethanol. They'll form that hemiacetyl. We'll have both of them. We'll have that alcohol and then the ether functional group. Again, together, that's called a hemiacetyl. They actually revert back to the starting point rather quickly. Now, there's a big exception of this. Major exception is when these are happening on a ring. So this earlier I kind of wrote out, or in the last section, in the last lecture, I showed you a structure of the sugar molecule. And this is the glucose, and it'll actually have this structure, and it's able to form this cyclic ring. And this is actually a hemiacetyl functional group that's being formed between these two elements here. And this kind of will, a lot of times, simple sugars will exist in the cyclic form because of the stability that it provides and the ability to form that chemical reaction with the aldehyde here and the alcohol, but it's all happening on one glucose molecule. That chemical reaction is happening on the molecule. And since these are so close and available to each other, they'll be able to kind of form that cyclic compound, the cyclic hemiacetyl group of glucose. Just like in that last slide, we can see that oxygen will attack the hydrogen, and then this oxygen will attack the carbon to form this closed bond group. An acetyl compound is a group, so here's a hemiacetyl where we have the alcohol and an ether, And just like we talked about before, if we add more alcohol functional groups, we can make these ether groups form together under the correct catalytic conditions. And so we can make a full acetyl by adding more or a different alcohol functional group. So this is just kind of talking about what we talked about in the previous lecture set, where we add two different alcohols together and we can make those ether functional groups. Same thing, we're just doing it on a different molecule. So these reactions still work even if we have another functional group below that carbon that's attached to the alcohol group. All right, this is drawn out as kind of a cartoon of three-dimensional ball and stick figures. Which of these two are going to be an acetyl? Is it the compound on the left or the compound on the right? And just post your answer in our Blackboard space. This is alpha-D-galactose. It's a type of sugar that we can consume. It's sweet. We can eat that and digest it. So I'd like you to tell me what functional groups are present on alpha-D-galactose that are shown here. So select the answer and post that also in our Blackboard space. Now that we've gone through some of those other functional groups with oxygen, I'd like to talk about thiols and disulfides. And these are kind of analogs to alcohol or different types of compounds that contain oxygen. And that is because they're in the same row of the periodic table. Sulfur is the same row of the periodic table as oxygen. And they'll also bond like an alcohol. And that's why we have, instead of the OL ending, we add the thi part of that to the naming. So the ethane is the backbone, and so we say ethane ethiol. So we add that thiol part to the back end of the word to tell us that there's a sulfur group in there. And again, it's an analog or a similar type of compound as an alcohol. So this is a 3-methyl. So we have 1, 2, 3, 4. So that's the butane backbone. We have on the third carbon, we're going to have a methyl group, which is shown here. And then the first carbon that's attached to a sulfur group, that's the 1 carbon. So that's the 1-butane-ethiol. So the full name is the 3-methyl 1-butane-ethiol. Here we have a 2-butene. We have on the second carbon the ENE ending for that double bond. And then on the 1 carbon is the thiol. These are different systematic names for thiol. A lot of times sulfur-containing compounds do not smell really great. So these two compounds here are actually going to be what a skunk scent is going to encompass. So these two thiols for the 3-methyl 1-butane-ethiol and the 2-butene-1-thiol, these two compounds are what make skunks stink. Important biochemical reactions that these undergo are they will form disulfide bonds, and these are going to form sulfur-sulfur bonds. And the reverse reaction occurs when we can reduce that. So it's a similar type of, so this is a oxidation when we have more electrons associated with sulfur, and then when we break that and add hydrogen, then it's a reduction. So for the same reason when we do that, create double bond, we are not making double bonds like we were with oxygen. Typically, these don't like to make double bonds because they're a lot larger than oxygen, and they'll prefer to make single bonds or sigma bonds between different compounds and groups. You might have, when you've maybe gone into a salon where it kind of smells funny, a lot of times where they use what is called beta-mercaptoethanol, and the mercapto part is going to be reducing some of these compounds, so they'll be able to break these bonds and reform them. That's what allows the proteins in our hair to be formed in those tight curls during that perming process. It's the reduction and oxidation of those sulfur bonds within proteins. And we'll talk about these thiols in the formation of different protein structures later in the semester. And that's what I'd like to stop here with the discussion of some of the different oxygen-containing compounds. In the next set of lectures that we'll do next week, we're going to get more into talking about some of these compounds and their relationship to acid-base reactions.